So I'm going to talk today about is TSS 8, Timesharing System 8. It was an operating system developed at CMU in coordination with DEC. And I'm just going to talk about its history, a little bit about the software, a little bit about the hardware, and then a short demo of the system itself that we have running here on this system. Okay, so TSS 8 started out as a just kind of a research project at CMU in 1967. They were looking into doing time sharing on small systems, where this system doesn't look small, but at the time it was a very small computer, very affordable as opposed to large mainframes at the time. They had assistance from DEC in modifying their hardware and developing the software. And it was eventually sold as a complete system starting in 1968 with the release of DEC's PDP-8i computer system, which is the predecessor to this PDP-8e here. This is this machine here came out in 1971. It ended up being moderately popular as an educational system. It was also used in business offices and various other places around the world. And by 1973, they had sold over 100 systems running this operating system, which wasn't a lot then, and definitely doesn't seem like a lot now. And so it never really became the most popular operating system on DEC hardware. But it is a very interesting little piece of history, and I'm excited that we have it running here at the museum. So, what is time sharing? As a contrast, let's talk about batch processing, which is still the dominant form of computing in the 1960s. You had a large mainframe computer. It was very expensive, and any time that computer sat idle was just money being thrown out the window. You had to keep the machine running. You had to power it. You had to cool it. You also had to, if you were, it was a large IBM machine or whatever, you were also paying rent on it, basically. So the idea was to keep the system busy, keep it doing something at all times. And batch processing was one way to do that. You as a programmer or a software developer wrote your program out on using flowcharts or a notepad. You punched it into punch cards using a key punch like we have over there. You had a deck of cards. You took that deck of cards, you brought it to a computer operator at your computer center at your university or your business, and then you gave that to the operator, and the operator said, all right, come back next week and pick up the results. And hopefully your program worked properly. Otherwise, you got an error listing, and you got to spend spend hours trying to figure out where your program went wrong. Then you did the same thing again, and you came back and you submitted your job. So other people did the same thing, and there would be a big queue of jobs, and so the computer would be continually busy. So this is an efficient way to use the computing resources, but it wasn't a very efficient way for users to actually use a computer, because the turnaround time was impossible. In contrast, time sharing was a mechanism via which a system was made available to multiple users at the same time, providing the illusion that every user had the system to themselves, when in reality they got a small fraction of a second at a time. While you were typing at the system, the computer would respond to you and then go off and service somebody else for a little while, and then somebody else for a little while, and then somebody else for a little while. This is very, very similar to the way today's modern multitasking operating systems work. Today you've got multiple processors even in your phone, but those processors are all being split up via around multiple tasks and jobs and things that are running on your phone or on your computer at the same time. That's the same thing as time sharing, basically. And since user input, you're typing at a teletype like that one right there very slowly. It was very easy for systems at the time to provide a response time that made it feel like you had that system entirely to yourself. So that allowed for interactive computing. You would run an editor on the time sharing system, type it in on your teletype, and compile it, run it. It would crash, and you would say, "Oh, I have to debug it." You'd debug it online. You'd run it again, and now your development time was measured in minutes or hours instead of days, as opposed to a batch system. So time sharing as related to TSS 8. So in the 60s, as I said, time sharing was the purview of large and very expensive systems like the IBM 7094, certain IBM 360 systems, the SDS 940, and the PDP-10. These were all systems that took up entire floors or rooms in a building and required special cooling. You didn't get to touch these systems. TSS 8 demonstrated that time sharing could be done on small computers like this machine right here, which operates on office power, doesn't require special cooling, takes up maybe a corner of a room instead of an entire room. CMU estimated that the cost of running a time-sharing system like TSS-8 was about a 20th of what it cost them to run a time-sharing system on the IBM 360-67 that they had at the time. And a single PDP-8i or a PDP-8e system like we have here could service 20 users with a mere 32 kilowords of memory. Just for a point of reference, if you have your smartphone and you open it up and you look at the icon, one icon on that screen on your phone uses up about 4 times the amount of memory in this entire system. Just so you can see how progress has been made, or maybe progress hasn't been made. An entire operating system runs in less memory than it takes to display an icon on your phone. And each user, when they logged into the system, got a virtual 4 kiloword PDP-8 system that they could do whatever they wanted to. And they could use the system without interfering with any other users on the system, and also without being able to bring down the system. So any development that they did was completely isolated from anyone else, and if their program crashed, it didn't affect the rest of the system. The PDP-8i was introduced in 1968. It was the successor to the straight 8, which you can see behind you over there. It's the one that's running chess. It's a 12-bit CPU. It's got a 1.5 microsecond cycle time, so that's about 667 kilohertz. It's a little over a half of a megahertz. 4 kilowords of memory, extendable to 32 kilowords, and all those were addressable as up to 8 4 kiloword fields. It could talk to a variety of devices: disk drives, tape drives, analog to digital, digital analog, industrial control systems, all kinds of different things. And like the original PDP-8, it was intended as a small, inexpensive computer. It cost about $12,000 in introduction, although as soon as you added peripherals and stuff like that, a complete system would probably cost you to $30,000 to $40,000. And as a result of the TSS-8 efforts at CMU, it had baked into the system an option called the KT-8i, which is the time-sharing option, which allowed the system to support a time-sharing operating system like TSS-8. What hardware do we need in order to be able to do time-sharing? There are certain instructions on a computer that you can't just let if you're sharing a system amongst multiple users, you can't just let anybody run them. For example, the halt instruction is an instruction that, when executed by the CPU, causes the system to stop. If any user could do that, then any prankster or anybody who accidentally, wrote a halt into their program would bring the entire system down, and all the other users on the system would be wailing and gnashing their teeth and getting very angry. Additionally, there are instructions called IoT or I/O transfer instructions, which are used to control the peripherals like disk drives and tape drives and all that sort of thing. And if anyone could execute those, they could just write whatever they wanted to on the disks or the tapes, and they could scribble over other people's data, which wouldn't be very good. Additionally, you need to be able to isolate users' memory. If one user can overwrite the memory of another user, then they can corrupt their state and cause bad things to happen. We don't want that, and so on the PDP-8i, the KT-8i and the MM-8i options provided that hardware. If a user tried to execute a halt instruction or an IoT instruction, their program would be trapped. Their program would stop running, and the operating system would take over and say, "Hold on, let me see what's going on here," and it could either abort the user's program or treat that IoT as a user request to access the disk or something like that and handle it in a specific way. And the MM-8i allowed the memory to be divided into 4 kiloword chunks that were all isolated from each other, so that users couldn't stomp over each other's memory, and that's why TSS-8 virtualizes a 4 kiloword virtual PDP-8 system. Additionally, you needed a storage mechanism, and the picture over to the side there is an RFO8 disk. That is a fixed head disk which allows very fast disk transfers, and that allows user processes to be swapped in and out of memory, because there's only a limited amount of memory. If you have 32 kilowords of memory and you're trying to support 20 simultaneous users, each using 4K, you can do the math there and say that you don't have enough memory to do that. And so when the system runs out of memory, the last user to run gets swapped back out. Their code is copied to disk, and then a new user's program is brought into memory and off of disk, and then executed for a small amount of time, and then swapped back out. The RFO8 was relatively fast at the time, and I've had a decent capacity, but still pretty low, only about 1 megaword. But that was used for swapping of processes and file system storage. And so I'll talk a little bit about the software side of TSS-8. So this is the actual operating system itself. There's a section, each there are 4 or 5 different sections of TSS-8, and they're each given a little name. TS-8 is the TSS-8 monitor. You can think of that as the modern kernel if you're familiar with modern operating systems at all. It is the kind of the executor of the system. It controls the low-level hardware. It schedules user jobs. It allows users to make requests to the operating system, and talks to the terminals and all of that sort of stuff. And this is the only portion of TSS-8 that is always in memory. It doesn't get swapped out to disk. It is always resident in memory and uses 8 kilowords. That's the entire operating system effectively fits into 8 kilowords in memory. SI is the system interpreter, and that is what is like the command line. It processes user commands, so you type a command to the operating system. SI is swapped into memory and parses it out and does the right thing. FIP is the file interface phantom. It handles file system operations, so if a user needs to read some blocks from the disk or write some blocks to the disk or other operations like getting directory listings, FIP handles that. It also has a really crazy, spooky name. And init is the initializer. It is loaded in when the system is brought up from power up. It loads TS-8 into memory. It can also do backup operations and patching operations. So once you log into your TSS-8 system as a user, you would see that what you get as a user is a variety of programming tools at your disposal. You have assemblers, you have basic Fortran, Algol, Forth, and Lisp, along with tools for manipulating files, copying things to and from tapes and paper tapes. And each user gets a small slice of the disk to copy their files to. Whatever work they're currently working on, they would generally get anywhere between 50 or 200 blocks on the disk. That's 20 or 30K of disk to work with. If a user program crashes, if you're doing your debugging, your program is stopped, you return to the monitor, and the monitor lets you debug your program or do whatever else you need to be able to do. And most importantly, when that happens, other users on the system are not affected. At the time, most PDP-8 code that it was in existence could easily be ported to TSS-8. Most PDP-8 software at that time expected to have the whole system to itself. But with a few tweaks here and there and some careful porting, it could be made to run on top of TSS-8. Assuming you could fit it into 4 kilowords, which as time progressed became less and less possible, which is one of the reasons why TSS-8 never became a huge success. The memory limitations were pretty extreme. But most of the early programs, the programming languages, were simply ports of earlier versions of those programs that ran off of paper tape or standalone. So what did it take to get TSS-8 running again? It hasn't been run on real hardware in a very long time, mostly due to the lack of RFO8 disks. The source code itself was actually saved in the early 80s. A hacker who went to Melrose High School in Maryland actually took home a PDP-8 system that was being retired from his high school, and the system administrator gave him a printed copy of the source code to the system, big stack of paper, and he took it upon himself to type it in line by line and saved it on that PDP-8 system onto deck tape, the drives right there, the little tapes there, where it sat for 20 years, and in the early 2000s he recovered the data from those tapes and released it to the internet. And if not for him, there probably wouldn't be much of TSS-8 left other than the memories and a bit of documentation. A few other hackers on the internet built a system to allow reassembling that code and running it under emulation. There's an emulator called SimH, which emulates a variety of hardware, including the DEC PDP-8. That's been basically where it's been running the past few years. But I thought it would be interesting to get it restored and running on the system we have here. Unfortunately, we don't have a working RFO8. We have a picture, earlier picture that I showed is of the one we have in our basement, but keeping those running is extremely difficult because the platters spin and there are multiple heads positioned over the disk, and when that disk stops spinning, the heads actually land on the disk, which, if you know anything about hardware, hard drives, is a bad thing. So they tend to just destroy themselves when sitting in storage, and keeping those running is not something we wanted to undertake. And I thought, well, we have an RKO5 drive. That's that drive right there. That's 2.5 megawords, or 2.5 megabytes, about 1.6 megawords of storage. So it's a little larger than the RF08 would have been. It's slower because, unlike the fixed heads, which are fixed in place, and so there's no seek times on the disk. So it's going to be a little slower because the head has to position itself to get to various positions, but it maps very well to the system because one track on that disk is 4 kilowords. So the swapping would be relatively efficient. So I thought I'd give it a shot, and so I took the work that had been done, the restoration effort to get it running under SimH, and I sat down and I modified the source code to, instead of using the RF08, it would use the RK05. The biggest challenge there was that with the RF08, you could tell the hardware, I just want one word, and it's located this word address on the disk, and it would give it back to you. Whereas on the RK05 and a lot of modern drives, it's sector addressed, meaning you have to get back a chunk of memory of 256 words at a time. And so the biggest challenge was adapting the existing code to this new model, which basically meant kind of emulating the behavior of the RF08 using the RK05. And I tested it under SimH, and after a few weeks of hacking and debugging, and just got to the point where we were ready to run on the real system. We wrote the pack out to the disk, and it booted up the first time and ran, and I was extremely happy. And since then, we have upgraded this system, so it now has 8 serial lines. TSS 8 supports up to 20 users, but we only have enough hardware in here to support 8. We have those 8 serial lines hooked up to a Cisco 2511 terminal server, which gives the telnet access, and that's behind our SSH gateway, tty.livingcomputers.org. We have guest access available, and we're working out how we want to give access, like permanent access to people. There's a limited number of accounts. I think, I'm going to mangle the number, but I think TSS 8 only supports 114 accounts. And then after that, you can't add any more accounts to the system. And given the popularity of some of our systems, that would run out pretty quickly. So we're trying to figure out how to give out accounts. So this is just a listing of the various programs that we have available on our system. There's a variety of basic programs. And I'm not going to go through all of these here. Instead, I'm going to give you a quick demo of the system. I'm going to log into it from my laptop here. So I'm going to log out here because there's already a user logged into this account here. And I'm going to log in. I'm going to type in the login command. This doesn't echo. You have to type in a sequence of commands. It's login, the user account, which in this case is 1,000, and then the password, which for the guest account is LCM+L. And that will not echo, and then once you're done, you're logged into the system. So I'm logged in over the internet, up in the sky, through here, to the system over here. So I'll show you a couple of things you can do. So if you want to know the status of the system, you can run the systat program. And that will tell you who's logged on, what stuff they're running right now, how many disk blocks are available on the system, and the uptime. So far, the system has been up 3 days. Our record so far is 2 weeks. Which is pretty good, I don't think they ever worked out all the bugs in the system, and certainly it's old hardware, so I can forgive it for crashing now and again. So you can see that there are currently 3 users logged in. One of them's here, one of them's here, and one of them's right here at the moment. If you want to see what programs are on the disk, what files are in the users directory here, you can run the cat program. That does a catalog of the disk. This terminal line is set at 600 baud, so that's why it's a little slow, but I think it kind of gives an authentic experience to the user. It's not slow enough, as slow as a teletype, but it's, it also helps mitigate the load on the system. If everyone was running at high-speed terminals, it would flood the system with interrupts, and it would run slower. So there's a utility called Putter, P-U-T-R, and that is the program used for interchanging data between different devices. So if I wanted to copy something from deck tape or paper tape onto the disk, I can use that. So for example, I can do a directory listing of the deck tape over here, which is named DTA0, and you can see the tape spinning there. I can also delete files from it. Oops, if I can type. And now it's going to go through and delete that file from the tape. Just going to have to think about it for a second. The tapes are spinning, and there we go, it's deleted. I can copy files to do that. I'll just copy that back. This is hello.pal is an assembly language program. PAL means the PAL assembler. So I'm copying that file back to the tape, and you can see it spooling up there. And I can type that file out to the screen. So we can see that this is an assembly language program. You can see the assembly code scrolling by there. And all this program does is print hello to the screen, and then it exits. The numbers flying by are the ASCII code for hello in octal. I'll exit out from putter here, and I will run the assembler, and we'll assemble that program. PAL-D is the assembler. It's the PDP assembler program, which takes PDP code. We'll give it hello, and we'll give it tell it to output to a file called bin. It's going to ask us if we want to provide any options to it, and we'll say we don't want to provide any options, and it's going to assemble it, and it's going to put the listing out on the console here, so we can see the code that it's putting together here, right here. This column right here is the actual assembly machine code that you would normally enter in manually, and it's building that up for us. And it is writing out a file called bin.bin, and that is the assembled program. It'll just take another second here for it to go by. All right, and we can use the loader, which is called loader, to load that program we just assembled into memory. And it's going to ask us for the input file that we want to load, and we're going to load bin. We don't have any options to specify, and it's going to load that into memory and return us to the monitor prompt here, and we can do start at 0, and it'll run our program, and it prints the word hello to the screen, which is what we wanted it to do. Let's see, other fun things are, so if you run systat, you can see who's logged on, which I did before, and we'll do that again here real quick. And so that teletype right there is job 1, K01, and I'm going to send that terminal a message. So now I send that message to that terminal there, so let that user know that I'm here and I'm talking from a laptop, and they could send a message back to me in the same way.
It really depends on what the machine is doing. If we can place it, if we can strictly software,